Dr. Ning, please start.
Sure, sir, sure. So, good evening, everyone. Myself, Priyank, and we have our third session with us. And we have Dr. Vijay Kumar here. So, Vijay Kumar is a full professor and founding head of the Biorefining and Advanced Materials Research Center at SRUC, United Kingdom, and also holds an adjunct professor position in the Research School of Polymeric Materials, Jiangsu University, China, Riga Technical University, UPES, Shiv Nadar University, and visiting professor at Cranfield University, UK. He did his postdoctoral study in material science and engineering at Iowa State University and received a PhD in polymer science 2009. His expertise includes the synthesis and processing of sustainable and functional polymer materials. He has been a PI or co-PI on several projects sponsored by BAE Systems, EPSRC, Royal Academy of Engineering, UK IERI, etc. He has published over 350 SCI journal articles, 2 patents, 52 books, and 40 book chapters on polymers and material science. His H index is greater than 84 with 22,500 citations. He has supervised 10 PhD students and 4 PDRA and currently supervises 11 PhD students and 2 PDRA. He sits on the editorial board of 20 plus SCI journals as editor in chief, example nanofabrication, biomaterials, and polymers horizon. Associate editor for applied nanoscience, advanced polymeric technologies, energies, and advisory board member for various other journals. I'm proud to say that he has been named among world's top 2% scientists in 2021 with a global rank of stupendous 122 in the polymers category and 133 in nanoscience and nanotechnology category. And he is among the most highly cited researchers list since 2020. I welcome you, sir. We are very happy that you have joined us from the United Kingdom. Thank you.
Namaskaram and good evening to everyone. At the outset, I would like to express my sincere thanks to the organizers for extending me the invitation, and special thanks to Anmol sir, who has been a dear senior of mine.
Thank you, sir. Thank you.
As the title of the talk suggests, I will be mainly talking about renewable materials, how we are transforming them from macro to nanoscale. So just to update you, I won't be snowing with you lots of research. It's more of a generic discussion. A little bit about SREC. SRUC is a premier agriculture and veterinary science institute that sits within the University of Edinburgh. We are the only land grant university in UK and always ranked #1 for agriculture and veterinary related research. We have recently started a new veterinary medical school that is newest one in last 150 years in Scotland. We work very closely with agriculture industries across UK and Europe. And in agriculture sector, we have generated more than 50 million of research funding almost every year. Over the past 15 years, my research has been focused on the core theme of synthesis and manufacturing of sustainable and functional composite material for advanced application. We have been developing different types of low CTE polymer composite for aerospace application, functional polymer composite, polymer for defense, especially bulletproof vest and some sort of sensing materials, wind turbine blade, one of current area of research for energy related application, recycling. We have been deeply looking into recycling of different types of material, especially agro waste, industrial waste, and plastic waste. Plastic waste indeed are one of the grave concern in the modern society. Hydrogels and membrane, we have looking into their use for biomedical application and water remediation. Then natural polymer, we are trying to embed natural polymer in one way or another. Then, and if I have to summarize the current research in three main domains. So we are looking into sustainability, manufacturing, manufacturing to additive manufacturing. As of today, we are going up to 3D printing to 4D printing, then self-healing polymers, material. Is a perfect example of self-healing as well as the materials from nature. We see if there is minor damage, they heal themselves. Along with this, all over the research focusing on climate concern, developing new materials, embedding new properties, different types of components are being developed, and all these are related to global climate change. As you might have seen recently, most of the countries have agreed that they will reduce their carbon footprint to significant extent, and every year COP-related international conferences are going on, and recently COP29 was organized in Middle East. Defined as any area's long-term weather pattern. I was just talking to Professor Anmol and we were talking about the weather. Weather is almost changing all around the world. Uh, One of the nicest example is Switzerland. There was a part where over the last several centuries, there used to be heavy snowfall, but last year there was no snowfall. And its weather is not impacting only one part of the world, but it's impacting almost all part of the world. And researchers are now focusing on how we can reduce carbon footprint. We know that Middle East, there is rarely any rain, but a few months back there was heavy snowfall in Saudi Arabia. So you can imagine how climate is changing and how weather is changing. You can see from this image. At the same time, in different part of the world, different types of weather or weather condition takes place. And one of the interesting cartoon I have come across is how is climate change happening? And the one interesting answer is human activity and human action, nothing else. So humans are totally responsible for whatever is going on. And through materials research, especially composites, we can reduce this impact. Bill Gates has once said that we always overestimate the change that will occur in next 2 years and underestimate the change that will occur in next 10 years. And in this direction, composite material, they are going to play a significant role. And even within composite material, especially nanomaterial, they are going to significantly change the material scenario. If we go, okay. So just let me know if there are any changes. So yeah, sorry, apologies for this uh, internet related issue. So I was talking about materials world. So in materials, we are seeing significant changes on day-to-day basis. If we see it from age-wise that we have been studying in our school days, history of material dates back to Stone Age, then Pottery Age, Copper Age, where we started learning the use of metals. Then was Bronze Age. It led to the foundation of metallurgy, alloys, and indeed initial step for industrialization of materials. Then Iron Age, that significantly impacted the human life. And the latest century is considered to be of plastic age and semiconductor age. And both these materials, plastic and semiconductor, they have become an indispensable part of human life. And now scientists are hybridizing both the semiconductors, especially physicists and electronics researcher, then polymers, more of plastic-based material. They are combining to come up with new material having properties that combine the combination of both the metals, non-metals, and make the materials more flexible. And in this scheme, it seems that with the advantage in electronics and technology, we are again coming back to the posture that we used to have in the early days of human civilization, but recently with more advanced technology. And if we have to classify materials. Subsequently, the composites made up of these. We can mainly classify materials into metals, ceramics, glasses, and then polymers. Metals, as all of us know, they are good conductor of electricity and heat. They are having good mechanical properties, strong enough, but they are deformable as well. So we can tune them according to our needs. Ceramics and glasses, more modern class of materials. They are thermally and electrically insulating, hard but brittle. We can see their example starting from our cooking utensils to our automotives. Then polymers, we see everyday example, our car, buses, clothes, packaging material, food packaging, all these, they are made up of more of plastics, or you can say polymers. If we talk about materials in particular, over 70,000 different types of materials are being produced all over the world, and this number is growing every day. And if we have to talk about automobile, it is made up of at least 1,000 materials. And to cope the different energy needs, scientists are also developing different types of transparent materials where we can control the light, temperature obviously as well. And especially this is really very important for Nordic countries where sometimes we have significant longer days in some part of the year while longer nights in another part of the year. So these type of materials are being developed for a number of applications. And then coming back to composite, a particular definition, composites are nothing but a combination of two or more different materials in which one act as a matrix, mean it binds the material, and the another act as a reinforcement. Reinforcement provides the strength. Here is the example, matrix can be any material, reinforcement that provide the strength, and the resulting material is called composites. In Europe, sometimes they call it composite. In US and UK, they call it composite. Irrespective of the pronunciation, the materials are application in number of way, and it's not a new term. These materials have been existing since centuries. Only last 100 years back, this term composite was coined back. And example of composite we can see around us. Human body is itself a perfect example of composite. All the green plants or trees we see around us, they are also part of composite, in which the main core is made up of primary wall, secondary wall. Cellulose provide the strength, lignin act as a matrix. Whatever color we see of a paper, that white paper is mainly made up of cellulose. If you see a brown color paper, it is a combination of both lignin and cellulose. Another suitable example of composite is granite that we see almost in every house. It has different names as well as depending upon its characteristics, it is called quartz, feldspar, hornblende, bentonite. So depending upon the composition, it can be classified into different stuff. Then our bone or body, they are also a perfect example of composite material, as I just talked. As a composite as well as man-made or synthetic composite. Starting from composite that is every day in our life, concrete, the material which is a building block for all the building. It is a perfect example of composite. Then in home, whatever table, wood, chair, they are also a perfect example of wood in which the adhesive, long ago it was Fevicol and these days it's more of epoxy or unsaturated polyester. They as a matrix. Then fiberglass, it is plastic matrix reinforced by glass fiber. And then another perfect example of ceramic and metal composite is aircraft engines and blades. It is interesting to know that composites are transforming the whole manufacturing industry, starting from aerospace to automotive to biotechnology. For example, 10 years back, the plane 777, it just used to contain 12% of composite material and mostly it was aluminum. But more recently, all the aeroplane parts and they are being made up of composite materials. For example, Boeing 787. Here we can see in this picture, most of the stuff is carbon laminate composite, carbon ceramic composite, aluminum sheet. You can see only in the part where then fiberglass and aluminum only in wings and outer part of the plane. Similarly, different another components are advanced aerospace or say fighter planes. They are also being made up of composite material and even radar materials. They are also being explored with different types of composite. But the journey of this composite material from lab to market is really challenging. The research we generally do in labs, in universities or national labs, that is mainly limited to technological readiness level 1 to 3. And there is a significant gap when this technology comes into real-time application. So this gap we generally call the valley of death. So nearly 1% of the research we do all over the world, only that is able to pass this valley of death and comes into realization that we see in the form of different products. So it's really important that we work very closely with the industries so that we can cater their needs. And how we can develop this composite material to meet the needs of the society, mean we make them carbon neutral, we can make them carbon negative, that will be really a great achievement. And also through use of different bio-based materials in the manufacturing of composite, we can reduce our carbon footprints and make the material non-biodegradable. So here you can see the plastic all over the world, non-biodegradable, and if we can replace these up to some extent, we can make a positive contribution to sustainability. And you might have heard that term sustainability or sustainable materials. This is the most frequent buzzword to scientific or non-scientific people. So what really sustainability is? According to World Commission on Environment and Development, anything that meets the needs of today's generation without compromising the needs of tomorrow generation comes under the category of sustainability or sustainable materials. Luckily, all the green materials we see around us comes under the category of sustainability, and our research team has been focusing on development of these sustainable materials since the last 10 years. We have been focusing on 6R principle that goes beyond the traditional recycle, reduce, reuse. We are focusing on remanufacturing, reinventing, and rethinking. For example, we take different biomass, extract different type of materials, for example, vegetable oils, again, develop polymer from it that can replace traditional synthetic counterparts. Base material, we are different materials, so we are making a complete circular bioeconomic triangle. And it's not that scientists have to play the role in making the material sustainable or contribute to sustainable manufacturing. In fact, all the three pillars of the society, they have to contribute. For example, social people have to reduce the use of traditional synthetic materials. We have also to look into economics, and then environment is the real key. You might be always hearing different types of buzzword, green manufacturing, cleaner production, closed loop production, circular bioeconomy, green manufacturing, and so on. But all of these terminology, they have the one core in themselves is the sustainability, how we have to reduce these carbon footprints. And bioeconomy is the newest buzzword in research, and especially in composite manufacturing field, where researchers are trying to replace almost all the traditional synthetic material with bio-based material. For example, the paint we use in our houses. Researchers are looking into alternative chemicals that can replace these paints. Especially, you might have seen these days more of herbal-based products for biomedical application, but they are now going from biomedical to automotive to aerospace. And here is the bioeconomy mean almost all of our precursor, they should come from renewable feedstock or renewable material or organic waste. Then again, coming back to the question, why there is so much thrust on sustainability, sustainable material, and their incorporation into so-called composites or biocomposite or bio material? The answer lies in front of us. Today, our oceans, they have more microplastics than fishes, and now they are becoming the part of our food chain. And then by 2050, our population will be double than what we are today. However, the land remains same and our resources are also same. So we must make use of the biorenewable resources, and also to meet the energy needs, we must look into renewable resources. If I talk about the Western world, US, UK, or Europe, nearly 20% of the energy we spent on keeping our houses warm. And as of today, we could not find a traditional alternative of woods because wood is perfect insulator, and these wood-based houses, they help maintain the temperature of the building. And till how long we can keep exploiting timber, because it take at least 10 years to grow a tree and then just 10 minutes to cut it down. So we have been looking into making use of different bio-based material that can serve as a alternative bio-renewable material to traditional timbers. We are looking into different component of plant cellulose that are generally considered as a waste. We are primarily focusing on cellulose nanocrystal, cellulose nanofiber. Why there is so much thrust? Because these materials offer a number of advantages. They are biodegradable, biocompatible, can be used for biomedical application. Their mechanical properties, if we talk about their strength, they can be easily engineered. Being a chemist, what interest to can easily engineer their surface chemistry and use them for a number of applications, starting from biomedical to again aerospace. And coming to polymers, in terms of composite, like I talked, there are metal-based composite, ceramic-based composite, and polymer-based composite. We are mainly focusing on polymer-based composite, looking into their surface chemistry and their different applications. We are mainly looking into high-energy capacitor for energy storage application and using polymer as a matrix. Why the interest on polymer as a matrix? Because they can be easily processed into large area. We can 3D print into desired shape. For dielectric applications, they are high breakdown strength and low dielectric constant. And then traditional ceramic materials, they have very high dielectric. So it is thought that the combination of both the materials leads to high dielectric properties, and it is a prime area of research thrust now for all the applications we see: battery, fuel cell, supercapacitor, or dielectric capacitors. And we have been mainly looking into different nature-inspired techniques, reducing the use of chemical so that we can reduce the carbon footprints for these applications. PVDF is one of the more, so far it is very difficult to engineer it with traditional chemicals. However, it is very sensitive to electron beam radiation thanks to sensitivity of these carbon hydrogen bond, so that they start immediately degrading when we subject. So we engineered PVDF polymer with electron beam accelerator, optimizing different types of radiation doses, radiation time, because if we go beyond a particular radiation dose, say 2.5 meridian, then the backbone start degrading, its molecular weight start decreasing, and we don't get any enhancement in the properties. Instead of using traditional chemicals to engineer the surface characteristics of PVDF polymer, we relied on synthetic mimic of muscle adhesive protein called dopamine hydrochloride. So it's a very nice polymer, easily soluble in water. Changing its pH, we can embed it or covalently bond it to any surface. It can be ceramic, metal, or polymer. Obviously, we have been looking into. And we have studied the dynamic properties of the pristine polymer without any treatment, and then the one engineered with the polydopamine. Here you can see there was significant enhancement in the lactic constant, almost 3 times than the pristine PVDF, and to the lactic loss was also very less compared to the pristine polymer. Still, we are investigating after 15 years of this initial work, but there is not a perfect reason for this, but we believe that it is more related to polarity and lot of hydroxyl group that are incorporated into the backbone of the PVDF polymer. Then during the publication of this work, we were approached by a German-based company. They wanted to come up with dielectric capacitors that is having dielectric constant at least more than 100. So building upon our preliminary work, we came up with the alternative approach of incorporating aniline monomer, and we were able to incorporate it in a very interesting way, where we were able to, if we have to talk about weight percent, to incorporate 12% of polyaniline. But interestingly, it was not that conducting, because if you see some of the research paper, when they add traditional polyaniline, then after 5% of addition, it becomes completely conductive. However, in case we were able to incorporate it into more of a nano form, that lead to such high dielectric properties. Here you can see the pristine PVDF polymer. Here is the nanoaniline enhanced dielectric polymer of PVDF. This technology has been transferred to industry, and also based upon the publication of this work, we were invited to summarize our efforts in chemical reviews way back in 2016. If you are interested looking more into the use of PVDF-based polymer for dielectric application, please feel free to go through this article that summarizes all the fundamentals related to PVDF and dielectric materials. Then we have been also looking into use of PVDF and its different component for both aerospace and biomedical application, developing different type piezoelectric or thermoelectric materials. In piezoelectric, we were mainly looking into aerospace, but researcher all around the globe, they are also looking into defense application, submarine, underwater applications. Our main focus is on health monitoring, whether it is of human health or structural health. In structural health monitoring, we have been mainly looking into aerospace material, and human health, we are mainly looking into biomedical material, because these two fields, they are very critical. Suppose a plane is flying and something happens in mid-air, we will not be able to repair it. So we are developing new technology where we can detect the damage in front and repair it out of self-healing material for such application. Similarly, for biomedical application, especially to look into heart attack or some another potential threat to health, we are developing new biosensor made up of these smart polymer-based materials. Then another area we are looking into piezoelectric nanogenerator, again for BA system, as well as another application. This work was also funded by Royal Society and BA System, which is one of the largest manufacturer of weapon in the world. Then we have been also looking into different types of energy storage devices and materials, but here instead of synthetic material, we have based material from lignocellulosic biomass. Interestingly, during COVID, we have also looked into the use for antimicrobial application for some of the face mask. In terms of battery, we are mainly focusing into recycling, how we can recycle different batteries. Obviously, we cannot replace the traditional battery with current ongoing research with sodium magnesium battery. They are still in the lab scale. So best way to address the problem related to batteries and their pollution is how we recycle their components. So we are developing different types of bio-based solvent, especially NADs that are known as natural deprotective solvent. They are able to recover most of the materials, and also we are making use of different types of enzyme or enzymatic chemistry, where we design some new enzyme with the help of colleagues from biotechnology, and those enzymes they are able to eat some of these components, and then later we can collect them. But one of the problem with the solution is we are not able to scale it up. Then we are also making use of different type of waste product. Here is the example of dairy based product where we are trying to generate biohydrogen from dairy waste water, as well as develop different types of component, for example, hydrogen, biofuel, and biochemical, as I mentioned. In terms of hydrogen, we are also making use of composite, especially carbon fiber composite, so that we can easily transport hydrogen. Hydrogen can be stored into different components. There are different methods. For example, physical method or materials physical method are traditional technique where we compress. However, in material method, lot of research is going on metal hydride and adsorbent. But along with these advantages, one of the challenges is how we store hydrogen and how we easily transport it, because the traditional vessel, they are made up of most of the high-tech metals. Cost is very high, and obviously their load is too high. So we are looking into composite, especially carbon fiber-based. They are lightweight and can be easily transported from one place to another. In the same direction, we are looking into development of different composite material, but we are mainly looking into engineering of polymer matrices. A lot of research efforts they are going on surface engineering of silica nanoparticle. Here, instead of modifying silica nanoparticle, we modified polypropylene again with the same interesting biomolecule polydopamine. And here you can see with the simple modification of polydopa, we are able to get higher mechanical properties. And imagine engineers these nanoparticle as well, we will obviously get more high mechanical properties compared to the traditional nanomaterials. So the rationale behind is like we should also look into other approaches, especially engineering of polymer-based matrices. Then in composite, we have been also looking into different nanocomposite materials, and graphene is one such material for which scientists were awarded Nobel Prize almost a decade ago. In spite of interesting properties, graphene is not water dispersible. We always need to make use of different harmful chemical for processing of graphene. That is one of the not able to see many products that are made up of graphene, although there is a still significant research efforts going on all over the world. So we have thought of using again that bio-inspired chemistry. We engineered it with dopamine hydrochloride. One of my master student way back in Cranfield, who has been doing PhD with Professor Ferrari, one of the pioneer in graphene in Cambridge. Sea surface engineered it with polydopamine, and here you can see a complete homogeneous coating. Then we use this solution. We checked its longevity as well. The solution after coating with dopamine hydrochloride, it remains sustainable until 6 months. And then we use those coating on textile to make them textile, conductive textile, and then later on smart conductive polymer. So we are lining up with the local London-based industry that is using our coating for making more of smart material in the near future. Similarly, we have been making use of different types of biomass-based material and graphene-based material for developing aerogels. They are really very important for carbon capture because the way deforestation is going on, it's not possible to reduce our carbon footprint plants or reducing the use of different materials. So we are also looking into different types of materials that can be used for carbon capture, and our prime focus is more on development of different catalysts and sustainable technology, and then we want to convert them into more of sustainable chemicals and polymers. And for some of the applications, we have also looked into the use of aerogel for biomedical application as well as food. Uh, Defense people all over the world, they work in remote areas, and sometimes they are not able to cook the food, or suppose if we are going for space application, the food cannot be cooked or it cannot be kept fresh for several years. So, however, if you are able to convert that food into aerogel, that sustain water and it will be ready to eat. And interesting thing is it does not lose its taste. So that is a really very important application of bio-based aerogel that are obviously made up of food or another grade materials. Then coming back to the initial discussion, we talked about the pollution. Air pollution all over the world is growing. There are several reasons: livestock, fertilizer, you name it, you will find in one way or another leading it to air pollution. And those who lives nearby Delhi, they know how grave the problem is, especially in the winter days. In fact, Canadian startup has started selling up bottled air to China, and this industry is booming, and India is also contributing to it because the air during winter it gets polluted so much that because of some health related issues, most of the people need to rely on clean air. So in this direction, we have been again looking into use of different composite, especially those are made up of bio-based materials. We are developing different types of nanocellulose, incorporating them with different photocatalyst as well as another materials. And here is one such example where we develop new bio-based filter and they outperform their synthetic counterparts. This research also made to the cover page of ACS Engineering Journal, I think last year. Then similarly, we have been developing trends of sustainable chemicals and polymer resin. I said adhesive. Instead of traditional adhesive, we are now looking into bio-based alternative of these adhesive in most of the wood industry or composite market. The resin or adhesive or binder, whatever we call them, depending upon which backgrounds we come from, they are mainly made up of unsaturated polyester resin or vinyl ester resin. However, we are looking into vegetable oil-based polymer resin, and the market is really huge, and it is expected to grow at a CAGR of roughly 8% over the next 5 years, and expected to be over 8,000 million crossing in 2020. That has already crossed, and it is supposed to be 13,200 million this year, and it is again supposed to increase. I need to look into the data what is for the next year, but here is one of the polymer we have developed from the soybean based oil. Soybean oil is one of the key ingredient of the food in Southeast countries, but in most of the Europe and US,
Cranfield.
several varieties of soybean oils are banned because of some inhibitive component in them. So it's no use of them. So we have been looking into making biopolymer from it. Here you can see the polymer we have developed is really very viscous, similar to the honey we have. So you can imagine we cannot directly use it for composite application or any other application. For this, we need to mix it with the reactive diluent so that the viscosity is decreased and it can be easily mixed with different reinforcement. And traditionally, styrene has been used as a reactive diluent for these applications, and knowingly or unknowingly in everyday life we inhale some amount of styrene because most of the components of our automotive industry they involve styrene. For example, styrene consumes only 9% of the overall world production, but it nearly count for 80% of the styrene emission. So next time when you sit in the car, make sure you keep most of your windows open, obviously, until it's very necessary because we inhale some amount of styrene every day. So to address this problem, we came up with the new polymer. We made use of vanillin alcohol that is mainly from lignocellulosic biomass or vanilla plant, and we engineered it and we came up with this alternative of styrene. We called it methyl vanillin alcohol. Those who work in the lab, they will find this chemical really very pleasant because it has a smell of similar to vanilla ice cream. We also studied its different mechanical properties. We compared it with pure MAES origin. Then we added different loadings of our reactive diluent MBA 10, 20, 30, 40%. And here you can see with the addition of this reactive diluent, the mechanical properties were found to significantly increase. I won't go into more detail, but they were as good as compared to the product we have compared with the traditional styrene based stuff. Similarly, amid COVID, we have started looking into use of traditional Ayurvedic medicines or materials that our forefathers have been using since centuries. Clove is such example that we use it. It has a compound known as eugenol that has really very good antimicrobial properties. So we prepared methylated eugenol from this material, and here you can see styrene. It just evaporates in seconds at a temperature of 30 T if we keep at isothermal. And here you can see we studied the temperature up to 9 hours. It was quite stable up to this temperature. Similarly, we have been making use of soya waste. Here you can see we have cultivated soybean. You get different product. It is soya flour, generally considered as a waste. We use it as adhesive and transformed again it into a biomedical adhesive. One of my PhD student in China, he has started company on this adhesive. Similarly, we have been looking into use of different biomass or different adhesive, a work funded by iBioIC, where industrial partners were Chembond and IGS. We have looked into the use of different biocomposite material for vertical farming. In vertical farming, all of these frames, they are mainly made up of steel or aluminium. However, in Europe as well as US, there are significant efforts, as I said, to reduce the carbon footprints. So the company, they wanted to reduce the carbon footprints, and we have been developing these materials for them. Similarly, we have been looking into different alternative of, say, soybean based adhesive, because if we have to use soybean based adhesive, we cannot use it in Southeast Asia, because here soybean oil is a necessary part of our daily food habits. So we have been looking into another adhesive as well. For example, tannin, again produced from different biomass. This work also made to the cover page of materials advances, where we summarize different efforts on tannin based materials. It can be processed using different technologies. We have been mainly looking into microwave assisted technology because it reduces carbon footprint as well as reduce the time. Here you can see traditional chemicals we use with different nasty chemistry. However, making use of traditional bio-based chemical, we can develop a new alternative of these solvents. Also, we have been developing new bio-based polymer or replacing traditional synthetic isocyanate based adhesive with tannic acid. Here is a bit chemistry, how we engineered different type of product and came up with the non-isocyanate based polyurethane. Polyurethane is mainly used for packaging application. So most of the packaging stuff you see, that is mainly made up of polyurethane and mostly a lot of isocyanate material, that is more of carcinogenic material. Similarly, we have been looking into development of different biorefineries. You might have heard about the petroleum refineries, but biorefinery refers to a system where we make use of different bio-based biomass and develop different types of product. We have been also making use of different waste stream, food waste, agriculture waste, looking into biotechnological approaches, focusing on different bioprocesses, especially microbial technology and genetic technology, and then again developing these bio-based fuel, bioplastic, and sustainable chemicals. Here is the example of different types of food waste we have taken into it and then developed different green chemicals. It involved different approaches. First is more standard based on biorefinery, where we directly develop different types of biofuel, biomaterial. Then we are looking into some of more high value applications as well, say bioactive compound from some of the materials such as algae, and then nanobiotechnology again for more biomedical application. Another important area we have been looking into making use of different waste, manure waste. So one of PhD student, he is looking into development of different valuable product from cow manure, especially packaging and other related applications. So in this direction, we have been also looking into development of different cellulosic nanomaterial, whether they are from cow manure or they are from different lignocellulosic biomass. Depending upon the application, we are able to convert them into nanofiber or nanocrystals. We have also summarized different cellulose-based nanomaterial for RSC published book series more on cellulose nanoparticle. These both the books, they look into their fundamental and applications, and they shows how much potential of these material is for lots of applications. You name it, you will find the application of these materials. We are also looking into the use of cellulosic nanomaterial for energy storage application. Significant such efforts are going on to development of wind turbine with the help of sustainable material, especially cellulosic nanofiber. These wind turbines, they are mainly made up of glass fiber as well as another synthetic fiber material. Obviously, we cannot completely replace the synthetic fiber composite, but we are trying to embed nanocellulose in sandwich structure where we at least incorporate some sustainability, and at the end of their life cycle, these cellulosic nanomaterials embedded within these wind turbine blade, they can initiate the degradation process. There are different applications of these cellulosic nanomaterial, green composite, rheology, you name it, you will find most of these materials in application. Then we have been also looking into how we make use of different enzymatic treatment to enhance the mechanical properties. So we engineer nanocellulose, then use polypropylene EJ matrix and our composite that were engineered with these enzymes. They showed enhanced properties. And again, one of the challenge that we have come across is the scale up of these materials. And similarly, we have been making use of different biomasses together with Professor Solekar in IIT Bombay. We have been looking into how we can make use of different biomass and then use it both for water treatment as well as use the leftover stuff for automotive application. Here is pic from IIT Bombay Lake, where they grow different types of biomass to clean the water. Then the problem was what to do with this biomass. So the PhD student, she developed different types of composite with these materials. Similarly, we have been developing different types of hybrid green composite to replace the traditional timber-based product or bio-based product, because we cannot keep growing the plants that will take 10 years to mature to provide the timber. So we are combining different industrial waste and developing different product. Similarly, way back in US, we have developed biodegradable container primarily made up of soya flour and biodegradable adhesive. The beauty of these material was they can be easily biodegradable. So at the end of their life, they act as a biodegradable. And we also made use of different thermoplastic materials. We have been looking into their synthesis as well as comparing them with their biodegradable component polymer. Here is one example of polybutyl succinate reinforced with microcrystalline cellulose and nanocrystalline cellulose. The rationale behind was generally when we talk about nanomaterials, we assume that any of the nanomaterial will give the mechanical properties far superior than the traditional material. However, in our research, we have found that it is not always necessary to go down to nanoscale route. Here, at least in case of nanofibrillated cellulose, we have shown that when we add 40% of nanofibrillated cellulose in polybutyl succinate matrix, we get a mechanical strength of nearly 560 megapascal. However, when we made use of microcrystalline cellulose, mean we never went down to nanoscale route, our mechanical properties were significantly higher compared to nanofibrillated cellulose. So from these results, we concluded that it is not imperative to go down to nanoscale because when we do a life cycle analysis, during that calculation, the energy consumption play a key role. So if we go down to this road, although material will be sustainable, but the whole process will not be sustainable, then it will be better to use a non-sustainable material. So we must look into different chemistry as well as materials perspective of material. So to say nano might not be the perfect solution for some application, especially if we talk about nanofibrillated cellulose. Similarly, we prepared these biodegradable composite using different cellulosic materials. We studied their biodegradable properties as well. Here you can see polybutyl succine matrix, 0 days. You can see pure matrix. It's a white color. 80 days almost completely degraded. And here is the composite. So mean we can develop the bio-based composite material that are fully biodegradable. Similarly, we have studied the different thermal chemistry, biodegradable studies. Here you can see starting from 0 day composite prepare the different loading 5% up to 15%. And then you can see after 80 days, they were almost degraded in natural environment. Meaning we can develop the composite material that are fully biodegradable. Similarly, like we talked about, there are bio-based foams and their traditional synthetic counterparts, synthetic polyurethane foam. Most of the packaging material, they contain polyurethane foam, obviously that have a lot of carcinogenic component within it. So we have been looking into making use of different bio-based material, especially hemp straw. Hemp is a crop that needs special license to grow in UK because of its lots of biomedical properties as well. Some of the component these are used for toxication related application. However, one of the problem when we grow hemp is its straw. So its stem is generally considered as a waste. We developed new hemp-based foam. We compared it with traditional wood, and interestingly, these materials they really show good properties compared to their wood-based component. So we have been working closely with a couple of industries based in UK who wanted to develop different type of component, for example cushions and so on. Based upon our work, there were a lot of media highlight as well on how we can make use of hemp, especially which is considered more of a notorious crop all over the world. Similarly, we have been looking into development of different antimicrobial material, their nanocomposites and nanocoatings. So we have been making use of different types of biomass as a matrix and developing different antimicrobial nanomaterial, embedding them in the matrix. Example is titanium oxide based nanoparticles, then combining it with different biopolymer for example, say chitosan, and then looking into different biomedical application. Similarly, we have been developing different types of face mask, clothes, and so on based upon the material we have developed. In addition, we have been also looking into the use of eugenol that I have previously shown that it has antimicrobial properties. So one of my former PhD student who is now professor in China, he developed a very interesting work where we looked into how we can transform this eugenol into a sustainable antimicrobial material. We made use of different component divinized benzene, butyl acrylate, eugenol, and then obviously using typical microemulsion chemistry, we made use of different coating type of material. And this article also made to the cover page of Green Chemistry RSC Journal in 2021. Also, we have summarized different efforts on making use of green chemistry, how we make use of green chemistry, develop different sustainable product or different biomaterials, starting from packaging to electronics and so on. So we have also summarized these different bio-based materials in an article in Chemical Reviews 4 years back. So if you want to get a flavor of different renewable nanocomposite, please feel free to go through this article that provides more of basic knowledge. Similarly, we have been looking into making use of different component, developing new nanocomposite for dairy health, especially also different bio-based products. So we were only institute in UK few years back to get this 21 million funding to completely transform the digital dairy chain. Then, as I said, one of my PhD student has been looking into making use of cow manure for different valuable product. So interestingly, he made news headline to all the newspaper across the world, including physicsworld.com. So we have been working closely with the University of Bristol on this work as well. Similarly, we have been looking into use of different advanced technique. As I mentioned initially, we have been looking into additive manufacturing via fused deposition modeling. Here is the again example of polypropylene, how we embed different types of component. Problem with traditional polypropylene material is there is shrinkage of the material. However, with the polypropylene, it remains strongly bonded to the matrix and its good chemical properties. However, large scale manufacturing is still a challenge. So we are developing new chemistries so that we can do 3D printing of large part. So through a UKRI funded work and partially funded by Cambridge Nanosystem, we have been looking into 3D printing and 4D printing of graphene and vegetable oil based polymer. Here are some of the component that we have 4D printed, incorporating some safe memory material within our component. Here are again some of the images or chemistry based stuff. We used AESO resin. Then we added some new molecules that are sensitive to light, and we were able to get the material in 4D printing format. Similarly, we have been looking into nano manufacturing, especially electrospinning and electrospray. You might have recognized this material curcumin. Again, it has a lot of biomedical characteristic, really good for health, antimicrobial properties as well. So we have been looking into its use for dressing material. We wanted to get rid of traditional dressings. We wanted to have a dressing that is once for all. You put it in once and then you need to know basis. You keep injecting curcumin powder in it, so you don't need daily dressing. Or still there are some parts of the world where people don't have access to the hospitals or medical centers. So we wanted to come up with this type of coatings for the bandage and so on. This work was partially funded by Monroe Technology as well, industry based in London. We have been also making use of different nanofiber, but this time mainly for structural health monitoring applications. Similarly, we have been developing different scaffold for biomedical application, but without traditional electrospinning, because problem with traditional electrospinning is it is time consuming, not scale up, very nice for lab scale work. So we have been exploring the use of needle free electrospinning, and then we have been developing different types of scaffolds starting from green nanoplatelet, polybutyl matrices, and nanofibrillate cellulose. And here are some of the another example. We have been looking into biomanufacturing for advanced biomaterial. We have been developing different biomass-based adhesive for biomedical application, especially for hernia mass fixation. This work was carried out close collaboration with Cambridge University Hospital. MedTech was our industry fund, and we are currently running some trials on animals on developed adhesive. Then, to summarize, to meet the long-term sustainable development as well as to reduce our carbon emission, we must use what we have not already used, and our oceans, our forest, our biomass, they are perfect resources, because if we don't use them wiser, we will not have a chance again to reverse the climate changes we are going on. And from scientific perspective, what principle we need to follow? Green chemistry principles are really very important to meet the circular economy goal or circular economy concept, starting from waste prevention to go for safe chemistry for accident prevention. Then, uh, just on a side note, we have been welcoming submission to some of the journal where I have been sitting on editorial board, and nanofabrication is a journal. Today it is having impact factor around 3, freely open access, no publication fees, as well another journal. So feel free to contribute your work to any of the journals. And last but not the least, there are many people who have contributed to the journey so far. It won't be fair to name few and leave others. So thank you everyone who has helped in the journey so far, and also the funding agencies who have been contributing to our work as well as very generously supporting us. So thank you very much for your time and patience hearing. And apologies again for mm, the problem we have got through this internet system.
Thank you so much, sir. We are very delighted to have you here. The talk was very enlightening. I would like other participants to ask any question if they have any.
I have one thing to say. Before and asking any question, please start your camera, then ask your question. So participants, now the session is open for your questions.
Hi, sir. Good evening.
Hi, good
Hello.
evening.
Sir, my name is
Yes, good evening.
Sir, can we call composite as functionally graded materials?
Sorry?
Sir, can we call the composite materials as functionally graded materials?
Yes, it will depend on what you are talking to whom you are talking, because the community is divided uh, on using the term composite.
Okay, that means you are saying like composites are also known as functionally graded materials.
Sorry?
That means you are saying that composite materials are also called as functionally graded materials.
Yes, so graded material will depend upon what are your component. So if one
Okay.
of them is acting as a, more as a adhesive or contributing to overall property, then obviously it's composite. But if it's not, obviously we cannot, because one of the material, it must act as a matrix. If there is no matrix, then it cannot be composite from a typical scientific definition point of view.
Okay, sir. Okay, sir. Thank you, sir.
Sir, good evening. My question is, like you talk about the different bio-based materials, and specifically nanomaterial is being used over there. So, sir, what is the environmental concern once they will get degraded? Then what will be the concern in terms of environment?
For biodegradable, the beauty is like there are no negative impact as of today. So if your material is made from bio-based resources or you are making use of green chemistry, then not. But for traditional nanomaterial, there are a lot of harmful impact.
Okay, is it the materials, nanomaterial is made up by the natural one, or is it like
Yes,
a
if
normal
material is made up from natural one, then no side impact. Even now, one of colleague in Harvard, he is now in Amazon Institute. He is looking into making use of different type of cellulosic nanomaterial for biomedical application, even for drug delivery and so on. So if it is from bio-based resources, obviously no harmful impact. But if it is from synthetic counterpart, then obviously there are some negative impact.
Okay, nice, nice. Thank you, sir.
So you may look into Professor Ali Kademi. He is one of the top guy looking into different bio-based material, or Professor Robert Langer in MIT. He just looking into all the biomaterials. You name, you will find some startup or some sort of product on using bio-based nanomaterial for especially biomedical application.
Thank you, sir. Thank you so much.
Hello, I'm audible.
Yes.
First of all, sir, your lecture is very informative, and I have a small doubt. As you said, you have prepared the cellular composites.
Yes.
Cellulose composite. Sir, what is the role of cellulose in that? Like you have used that in the practical application. So what is the role of cellulose in that? Why we are not
Cellulose
using cellular
provide
as such?
Cellulose provides the mechanical strength. So we have used polybutyl succinate as well as I think in one work we have used polypropylene as matrix. So to enhance the mechanical properties, cellulose is the key material, especially when we go to nano route for some of the applications. Obviously, in one of our work, we find that we don't need to go to nanoscale.
Okay. One more, sir. Cellulose have less solubility. Then how can it be cost effective? Like, what are the green solvent we are using to make it soluble?
Yes. So if you have to use it for biomedical application, then no concern. But if you are used to it for automotive application, then obviously you don't need to make use of these natural solvent, because as of today these natural deep eutectic solvent I was talking, they are not commercially available. We are just synthesizing them for some of the biomedical application we are looking. Otherwise you rely on traditional acid chemistry. You use basic chemical like sodium hydroxide, and then you do the pre-treatment, and going for nanoscale route you use acid hydrolysis method.
Okay, sir. Thank you so much, sir.
Anyone else who would like to ask a question?
Hello.
Namaskar, madam.
Anji, namaskar, sir. Sir, very good morning to you. And you are sitting in very smart building. And I want to congratulate you, sir, for such a mind-boggling session. And you have discussed the use
Ma'am,
of
thank you, ma'am. Thank you.
composites from, household packaging material to defense to energy storage devices to energy harvesting devices and whatnot. So how a person can be involved in all such problems simultaneously, sir? What is the,
No, no,
motivating
no, ma'am,
behind?
you are too kind, and Indian, they survive. We have to survive when we are outside India. So
No, sir, no. You have
it's
made us very proud for working for only 15 to 20 years, and you have done such a wonderful job. And I hope that your talk will, initiate different problems in different minds of all the researchers which are sitting here. Such a nice talk, sir.
thank you, ma'am. Thank you,
And
ma'am.
definitely, I think most of the participants, they would be trying to interact with you independently also, so that they can gauge how to do or how to, use these green materials especially. Thank you so much for your session, sir. Thank you.
Thank you, ma'am. Thank you.
Anyone else would like to ask a question?
I think so. Dr. Vijay, we are really very thankful to you that you have spared your time and enlightened all of us with this remarkable session. Thank you very much, sir.
Thank you, sir. Thank you for the invitation.
Thank you. I think Mayank, we will start our next session at 7:30.
Sure, sir, sure. I would like to tell all the participants that they can come again. We can take a break for 5-7 minutes. We'll start our session with